All right, we are continuing on here in our journey through 14. We are nearing the end of it. Thank goodness, here 14. All right. So earlier this morning, obviously, we kind of finished up talking about buffers. Was there any questions on sort of buffers, how to do the calculations? So again, the main take home of sort of the buffer calculations, and again, places where students sometimes go a little wrong is if you do choose again to do the ice table, you got to make sure you got the guys on both sides there. So it is a buffer. We definitely want to make sure that we do use moles when we're adding any type of acid or base to the buffer. And then we want to convert back to molarity after that first ice table. So for the most part, if you are going to do kind of that first ice table in moles, then using the total volume like we did, we want to convert it back over when it's all said and done. You obviously could use the Henderson-Hasselbalch equation without doing the ice table. And again, you just want to make sure you get obviously the base over the acid, and you want to make sure you're using the pKa value when you're using the Henderson-Hasselbalch equation, and you hopefully should be in good shape. So the next thing that we're going to talk about, which is really one of the big issues here, or big things, is actually titrations. So we're going to talk about titrations. Now, titrations, as you may know, or maybe have done titrations before, I think they still do that in Chem 50, I think, right? So in a titration, we typically add a solution, for example, of known concentration to a solution of unknown concentration. And the idea here is if we sort of know pretty much the concentration of one of those solutions, we could use our volume there and do some stoichiometry and really figure out the molarity of the other solution. So a lot of times when we do this, we use a burette, right, to do that. And we got a receiving beaker or flask on the bottom, and that obviously is what we have going on here. There's our burette. There is our flask. And in the case of sort of acid and base titrations, we can, in certain cases, have the base up here in the burette, or you could obviously have the acid up there, and vice versa down here. You could have the acid or the base down in the flask or the beaker. We usually do a titration until we reach what is known as the equivalence point. And the equivalence point is really the point where the reaction is complete. And in the case really of an acid-base titration, when you hit the actual equivalence point of your titration, that is really the point of the titration where the moles of the acid will basically equal the moles of the base. This is also why they are sometimes called acid-base neutralization reactions, because they kind of neutralize each other at that point. In most titrations, or in a lot of titrations maybe that you have done before, you typically want to kind of stop at that point. And to help you sort of identify that point, we oftentimes use an indicator to help us do that. And that is a substance that we could add to the flask, for example, that will change color, like here. Probably something like phenolphthalein you maybe have used before. Phenolphthalein is colorless in acidic solutions. It's actually colorless in neutral solutions, and it turns everybody's favorite color of pink, right, in basic solution. Yeah, as we'll talk about at the end of this chapter, but pretty much indicators work off of a specific pH range. So something like phenolphthalein that you probably used when you did those titrations works actually from a pH range of like 8.3 to like 10-ish in terms of pH. And around 8.3, it's actually still like colorless actually at that point. And then it becomes kind of pink and various shades of dark, super dark pink as you go there. Perhaps when you did your titrations in Chem 50, they yelled at you that, hey, you need to stop at like the lightest color pink you could see, like you got to hold it up to something white to kind of see the pink type of thing, right? So, and that's really because that would put you, as we'll talk about here, kind of on this side of the pH, which is probably really close to the equivalence point. If you went super dark pink, like I like to titrate, that might put you over at that part and you might actually miss the equivalence point. We will also talk about the fact that, well, really, it doesn't really matter as long as you're really careful, and we'll talk why that is in just a second. We'll also talk why, if you actually have done a titration before, a very common phrase that you also hear when people are doing these type of titrations is, I just added 1 drop and the thing went like super pink. It was like no pink. I added 1 drop and now I have a beautiful shade of fuchsia going on right there, right? And we'll explain why that actually does happen and why it's not so critical, maybe, if that is the situation. We also sometimes will hear a phrase that are sometimes referred to as the endpoint of the titration. And the endpoint of the titration is basically where you lay it up and go, I'm done, pretty much. And if you do a good titration, your endpoint and equivalence point should hopefully be very close to one another as we go through it. All right, so let us first talk about, we're going to talk about really 3 different types of titrations of what's going on. And we're going to look at the titration kind of all the way through the titration and even what happens as we go past the equivalence point, if we should keep adding, you know, base or something like that. Maybe you did that when you emptied your burette, just like drained it all into there. You basically just shot way past it. So the first type of titration that we're really going to talk about is a titration between a strong acid and a strong base. So this could be something like hydrochloric acid, which is obviously a strong acid, plus a little sodium hydroxide, which they call that a strong base. And we will get a little H2O going on there and a little sodium chloride on the back end there. And this is the overall reaction that is going on. And what we are looking at in the picture here is what is sometimes referred to as a titration curve. So this is a titration curve, and on a titration curve, we have usually the pH there on the left, and in this case, the volume of sodium hydroxide on the X. So just for orientation purposes, in our burette would be our sodium hydroxide. In our beaker, we would have our hydrochloric acid, and we are obviously adding sodium hydroxide to the acid that's in the beaker. And that's why on the X, obviously, we have the volume of sodium hydroxide that we're adding in this particular case. This is a typical titration curve, which sometimes people refer to as like an S curve kind of going on there. And all titration curves pretty much have 4 sort of distinct areas that we look at. The first area is right here, kind of like before we start the titration. So this would be before we actually add any sodium hydroxide in this point. The second sort of part on the titration curve is like from the very first drop to just before the equivalence point. The sort of third important part on the titration curve here is actually right there at the equivalence point. And then the sort of 4th area that we oftentimes will look at is sort of after the equivalence point. So we're going to kind of talk about each of those spots here, and we're going to talk about how you go about sort of calculating the pH anywhere along this curve at each of these spots. So let us start in this titration first off with what happens at, say, point number 1 there, which is really before we add any sodium hydroxide in this case, right? So before we add any sodium hydroxide and really start the titration, basically we're looking at whatever is in my beaker, right? And what's in my beaker or flask in this point is what thing? It is the acid, right? In this example here is the hydrochloric acid that is in there. So if I wanted to calculate the pH here of hydrochloric acid, I could do that because I know hydrochloric acid is a strong acid, which means we would expect it to, as we've talked about a number of times, completely break apart into H plus and Cl minus, which basically means if I know the concentration of my hydrochloric acid, I will also know the concentration of my H plus. And that really is all I would need at this point. to calculate the pH, because now I could just go into the pH is equal to the log of the H plus. Although it is a titration, we have not added anything, so we're not running into any issue like we talked about this morning where we're adding volume, right? Because we could just use the concentration of the hydrochloric acid in this case, right off the bottle or whatever we use, and go really right into our pH equation there. Any questions on that? We would obviously expect it to be acidic at this point. And if we look back on our graph, that is definitely what we see there with like a pH in this particular guy of 1. So that's definitely acidic. Now, at step number 2, we're ready to now sort of start adding some sodium hydroxide. So a couple of things we want to think about when we start adding sodium hydroxide. First off, we are going to get a reaction that's going to occur obviously between the hydrochloric acid and the sodium hydroxide, which is the one I wrote up there on the top. We are also now adding volume, which means we do need to actually do an ice table here to figure out, what is happening to our hydrochloric acid. So we do need to do an ice table, and we would have to do it like we talked about this morning in moles, because again, pretty much in a titration, as I mentioned earlier, you're doing nothing but continuously add volume, which means your molarity is continuously changing through the titration. The only thing that is not changing through the titration is obviously the moles. So we want to always kind of do this first ice table here in a titration situation. Once you've started the titration, you always want to really do that first titration in moles. And much like we did with the buffer, once we're done with that first titration, we want our first ice table, we want to convert it back into molarity. So let's take a look at sort of what that would look like. So let us do like this. So let us look at step number 2 here, and we are starting the titration. We are definitely before the equivalence point. So as I mentioned before, you will definitely need to do an ice table. So we're going to do our reaction, which is the one I wrote on the other page there, HCl plus some sodium hydroxide. Going to give us some water and a little sodium chloride here. We are again going to do this in moles. And just so we're very clear here, I'm just going to make up a number. Yeah, so that is where this number came from, just to keep a nice, simple, easy number to look at. I'm going to start with 4 moles of HCl. And again, I just made up the number. So what we want to think about is this. If we are before the equivalence point, this is clearly what we are starting with. This is clearly what we are adding from the burette. Should the moles of the sodium hydroxide be less than, equal to, or greater than the moles of acid if I am before the equivalence point? It should be less, I think is what you said. And that is correct, because the way you can remember that is when we reach the equivalence point, they are equal, right? So the only way to get the guy that you're adding to be equal is it's got to be below, and then it becomes equal, right? So since we're not at the equivalence point, we are less than that. So the moles of the sodium hydroxide in this point should always be less than the acid that you're starting with. And again, I'm just going to make up the number. I'm just going to go with a good number of 2 here. And that we're going to say we added 2 moles of sodium hydroxide. Our other side here is just going to kind of zero out. Our change here is going to work very much like sort of the buffer ice table that we did earlier. At this point, we could look at the 2 reactants, and we should see that which one is like the limiting reagent at this point. It should be the sodium hydroxide. The simple answer is it's the smaller number, yes. So it's like the limiting reagent at this point, which means you have plenty of the HCl at this point, which is like the excess reagent. So the change here is going to happen is it's going to basically chew up all of that sodium hydroxide you just added in this titration. So we will, once again, very common with tables where we use moles, actually use a number for the change part. So this would be -2, -2. And again, we would have like a +2 moles over here. That means when we do reach equilibrium here, we will end up with 2 moles of this guy. We'll end up with nothing of the sodium hydroxide, and we will end up with 2 moles of the sodium chloride. First off, any questions on the ice table here? Now, just like we talked about this morning, we want to really convert these guys back to molarity because it will make some differences here, the future calculation that we do. We would convert these guys back to molarity by, again, using the total volume. So what we're talking about here in the titration is the volume of the HCl we started with and how much sodium hydroxide we added into the beaker from the burette. So we would then take this guy and convert it back to molarity by dividing it by the liters, which obviously would be the total volume at this point in the titration. Now, if you are not sure what is going on at this point, you do want to look at what you got left over here. You do have some sodium chloride. We do have some hydrochloric acid. Is that a buffer? I heard no. And I agree with you. It is not a buffer, by the way. Although they are related to each other, this is not a buffer. Why? Yeah, because HCl is a strong acid. So a very common mistake people make when they do titration problems is, I got 2 numbers. That Henderson-Hasselbalch uses 2 numbers. I'm just going to lay it into there. So this is definitely not a buffer situation. So you got to really be careful that you can end up with this situation and think it's a buffer, and you'll put it into that equation and obviously get the wrong answer. Not sure how you do that without a pKa value, but maybe you get creative, who knows. But so it's really not a buffer. So we do really want to analyze what we got going on. Let's start over here. This is obviously our salt, right? And are we concerned with this salt doing anything to mess up the pH? It will not, right? Because it does come from really a strong acid, strong base. It's a neutral salt. So really, we're not even concerned basically of anything that's over there. So really the only thing we are left with is this HCl, which is a strong acid, right? And obviously that is what's going to basically make the pH that we got at this point. The good news is we have the molarity here of our strong acid, which means pretty much at this point, that is most likely going to be your H plus concentration. And then you could go right into your pH equation at that point. So at the start of this type of titration, all the way until you get to the equivalence point, you do need to do 1 ice table. The ice table does need to be done in moles. And really the purpose of the ice table is to figure out how much of that strong acid you got left after it's reacted with the sodium hydroxide. All the way up through there, your strong acid should be the excess reagent. The sodium hydroxide being added should be limited all the way through there and should be used up. So 1 ice table in moles, convert it back to molarity at the end. And again, the reason you'd want to convert it back to molarity for sure is the pH is minus the log of the H plus concentration, not minus the log of the moles. So if you leave it in moles, you will get the wrong answer. So very important to convert that thing back to molarity at the end of that table. Any question on that part of the titration there? So clearly we see we're really kind of bringing down, obviously, right, the H plus concentration, which means as we continue to add the sodium hydroxide, what should be happening to the pH? pH should start to be going up, right? Because we're kind of bringing down the H plus concentration, and that should bring up the OH minus concentration. And that's actually what we see here. We kind of see, a gradual sort of rise there in the pH as we're approaching the equivalence point. As we near the equivalence point, which is what we're going to talk about next, we're really, if you think about it, sort of using up the H plus concentration or acid, bringing up that base until they're about even, right? So as we kind of come this way, we're going to have less and less of the H plus at that point, and we're going to start to see a much bigger jump in the pH as we definitely get towards the equivalence point. And in most cases, what you actually see is what we see here, is you see a pretty big jump to the equivalence point in terms of the pH. And then you actually, as we'll talk about, see another jump in pH after the equivalence point. But what we do see happen as we approach the equivalence point is, if we look at this graph, it is going pretty vertical. Yes, as we go to the equivalence point there. Bad choice of color, I see it. So as we approach that equivalence point, it is getting pretty vertical. What does that mean if we approach the equivalence point and it's getting pretty vertical? When I reach the equivalence point or come towards the equivalence point, does it take a lot of volume to change the pH a lot? It doesn't, right? Because pretty vertical, no matter where you draw the line, if you go straight down, you're kind of in the same spot, no matter where you pick on that vertical axis. Which means, although we're not adding a lot of volume, there is some big pH change happening as you go through the equivalence point. So let's revisit the question of, I added 1 drop and my thing went super pink. When we think about phenolphthalein, which is 8.3 on the pH scale to 10, this being super pink on this end, this being colorless, you're approaching the equivalence point, you add 1 drop. That is enough to move the pH a lot, right? Which visually you will see it go from like no color to, oh shoot, super dark pink. I need to throw my titration away. Hopefully your teacher didn't make you do that. But do you need to throw your titration away here if you just missed it by a drop? No, because even though you may be super pink, your drop only puts you about here, yes, or wherever it may be. You're still, in terms of the volume for the equivalence point, pretty much in the right location. The reason they may make you redo the titration is they don't know if you really do titrate like me, where you just open the thing up, let it drop in there, and at some point shut it, gave it a shake, and said, hey, cool, I'm pink, I'm done. Because you could also be very dark pink and actually find yourself way over here, right? Which then means you are very far away from your equivalence point. So if you are really careful as you're doing a titration and you're doing it kind of drop by drop as you approach the equivalence point, and you maybe miss it by a drop or 2 even, it wasn't really that big of a deal. Your calculation would still come out the same. Hopefully your teacher didn't make you again redo that. That's why, usually they'll say it's more important the volume to reach the equivalence point between your different titration trials are usually about the same, then you'll be in good shape. But again, if you really weren't careful and opened it up, I was always the first one done titrating in high school. Yeah, well, you said pink, it's pink, I'm done. So you open it up and you really weren't careful, you really could way overshoot the equivalence point. And there would be no visual difference between kind of the color that you would see there. It gets very dark pink and it stays dark pink. So, if you're really careful in future titrations, you need to stop at the equivalence point, and you feel like you missed it by a drop or 2, is not a big crucial deal. You'll be fine. But if you're not careful, you should maybe redo it and stuff like that. Any questions? And that answers the age-old question of why I added 1 drop and it went crazily pink on me. Yes. All right. So now that we added the 1 drop, it went crazily pink. I decided to drop my pH titration here, and we're actually at the equivalence point. Let's talk about what happens at the equivalence point in this type of titration. So once we are at the equivalence point, we obviously are still having a reaction that's occurring between hydrochloric acid and sodium hydroxide. And we'll still get our water here and our sodium chloride. There we go. And again, I'm just going to make up the numbers. We would obviously want to do this in moles. So I'm going to, again, just pretend we are starting with 4 moles of HCl. Again, this is what we're starting with. This is what we are adding. Now that I'm actually at the equivalence point, how many moles of sodium hydroxide should I have? should be exactly the same. That's basically your definition of equivalence point, same moles. So that is 4 moles there in my example. This would be 0. You really can't go wrong here. There is only one number to choose from, and it is the same number. So pick that number would be a good move. That is going to get you zilch of that, 0 of that, and a little 4 mole action of that, which obviously we could convert back to the molarity at this point. So what we see here at the equivalence point in this type of titration is we are basically left with just sodium chloride, right? We would expect the pH to be what in this case? We'd expect the pH to be 7, or just the P. We'll add the H there. So the pH there will be 7, because basically no matter what combination of strong acid, strong base you do in a titration like this, at the equivalence point, the only thing that will be there is some water, which is not going to mess up the pH, and you will be left with a neutral salt. So the good news in this type of titration is there's really no calculation you need to do. You just write pH to 7 and be happy with your answer at that particular point. Any questions? This is also why when they specifically talk about a reaction between a strong acid and a strong base, they are sometimes called acid-base neutralization reactions, because basically what you're left with is water and a salt that's really not doing anything other than floating around having a nice day. Any questions on that there? Let's talk about, for this type of titration and other titrations we're going to talk about, let's talk first off about the equivalence point in terms of how would I know the volume I need to reach the equivalence point if they do not tell me? How can I figure that out? So let's just say randomly here, we are doing like 50 milliliters of 0.2 molar HCl, and we're titrating it with 0.2 molar of sodium hydroxide. I want to know the volume to reach the equivalence point. How could I figure that out? Any idea? Well, let's just say we're not actually physically doing titration, but we're just kind of doing the calculation part. How would I know? You absolutely could use M1V1 equals M2V2, and you could use that because it is a one-to-one relationship here. If the titration was not a one-to-one relationship, you could not use that, because although we use the M1V1 equals M2V2, it really is stoichiometry that we're doing there. And it only works because it is a one-to-one relationship. So you absolutely could do that. You could also do a regular stoichiometry problem where you convert your volume of HCl to liters and use the molarity of the HCl to convert to moles of HCl, which if I grab my calculator here, 0.05 times 0.2 gives me 0.01 moles of HCl. It is a one-to-one relationship. 1 mole of NaOH, 1 mole of HCl. Those guys cancel, gives me 0.01 moles of NaOH. Now I have the moles of NaOH and I have the molarity of NaOH, right? Molarity is moles per liter. And if we rearrange, liters is moles divided by molarity. So that would be basically 0.01 moles, dividing it by our 0.2 moles per liter. That gives us 0.05 liters, or 50 milliliters of sodium hydroxide would be needed, which is the long version of M1V1 equals M2V2. You can basically take 50 times 0.2 and divide it by 0.2, and you end up with 50. Yeah. Also, whenever the concentration of the acid and base are exactly the same, like in this case, and it is a one-to-one relationship. You need the exact same volume to get yourself to the equivalence point. Lastly, if you don't know any of that stuff, but you do know the idea that when you get to your ice table here at the equivalence point, you will know the moles you should have, right? Because it should be equal. You then could just jump to this part and you know the moles you have and the molarity of it, and you can solve for the volume. So there's multiple ways you could do it, but probably the easiest in most cases is to use M1 V1 equals M2 V2. Again, as long as it's a one-to-one, it's all good. The reason if it's not a one-to-one is the stoichiometry here technically is different, right? So you would actually need a different amount. So you just got to be careful on that. Most titrations that we sort of talk about in this class and most times is like a one-to-one relationship, but it may not be. And if it's not, you kind of got to do the stoichiometry part of it. Otherwise, you would get the wrong volume. The reason I'm going through all this is in a lot of titration problems, they may oftentimes not actually tell you the volume to get to the equivalence point. They just may simply ask you, what is the pH at the equivalence point? And you do need to figure out the volume so that you can, when you get, for example, to the ice table, convert it back to molarity correctly using the total volume. So, you know, sometimes you need to actually figure that out. Any questions on how to figure out the volume to reach the equivalence point? Okay. All right, so the good thing, like I said on this one, is you really don't have to worry about any of that because the pH in this type of titration should always be 7. Let's talk about what happens though if, you know, that thing turns beautiful pink. It does not dissuade you to stop. You're like, I still got a lot of like sodium hydroxide up there in the burette. I'm gonna go. And yes, you should keep going to get the rest of the curve up here. So let's talk about what happens after we pass the equivalence point. So clearly we see there, as we talked about, a jump that typically occurs in pH as we go past the equivalence point. And that's essentially because at the equivalence point, you got equal amounts of both. And if you decide to go past the equivalence point, you're basically just adding more base, which means you're adding more hydroxide really quickly. And that's why we're going to see that kind of spike in pH is going to happen after the equivalence point because your solution is kind of equal. And then you just spiked it with a lot of hydroxide really quickly. So at that fourth part of this titration, which is after the equivalence point, we still have a reaction that occurs. So we still need to do our hydrochloric acid plus our sodium hydroxide here. Same reaction we've been talking about. And once again, I'm going to use my made up number there of 4 moles. But now we are definitely past the equivalence point. So should the moles of the sodium hydroxide be less than, equal to, or more than the HCl? It should be more than the HCl at this point. I'm just again going to make up a number of 6. Seems like a nice number. Now, what happens at this point, because we didn't stop at the equivalence point where they're equal, there's actually sort of a change that occurs. Which one is now like the limiting reagent at this point? Yeah, so this guy is now like the limiting reagent, and this guy is the excess reagent. And now basically the change is actually going to be the HCl because we no longer have enough HCl to handle all that incoming base that you did. So the change here would be -4, and a +4 situation. That means we got nothing going on there. We got a couple of moles of that guy. We got 4 moles of this guy. Once again, like normal, we will take our total volume there and convert it back into molarity. And you should never overlook your ice table because if you ever find yourself lost or not sure what's going on, the ice table does give you a lot of important information. So we can just simply circle sort of what we got left and we could analyze what that is. The first analyzation should once again tell us, is this a buffer at this point? The answer is no, it is not a buffer at this point. Again, even though you got 2 numbers, they are not related to each other, right? One sodium hydroxide, one sodium chloride. That is not a combination that's related to each other. Is your question? Are good? Well, it's really not a buffer, because in order for it to be a buffer, right, the relationship that you have to have is either a weak acid and its conjugate base, so they have to be related to each other by 1H plus, or a weak base and its conjugate acid, which has to be related to each other by 1H plus. So in terms of relationship here, they're really not related to each other in that sort of Bronsted-Lowry definition. And secondly, you know, even though we do have a base here, that base is also obviously a strong base. So you can't have a buffer that's a strong base. And as you correctly said, the last thing would be sodium chloride is neutral. And it's neutral really because it comes from something that's strong that obviously eliminates it from either affecting the pH or anything like that. So when we look at this, this is our salt that we've seen before. And as we've analyzed before, this salt is still, even though it's at this point in the titration, still neutral, right? So not concerned at this point about this guy doing anything to our pH, which again brings us down to just really this guy being left over. And that guy is sodium hydroxide, which is a strong base. Which means if I want to calculate the pH of this solution from our ice table here, we will actually have the concentration of this strong base, which will actually give us a concentration of hydroxide here. That's an important thing to remember. This is hydroxide, which means you can calculate the POH, which is still not the pH, right? And then you can go to the pH at this point by subtracting 14, basically. So once we go past the equivalence point in this type of titration, essentially we're just dumping base in there and we're just adding a lot of OH minus. And again, that's why we do see that jump past the equivalence point. At some point, you sort of max out your OH minus and it will kind of plateau out, which is what we kind of see at the very top of the curve where it kind of plateaus out. You know, you kind of max out there in terms of the amount of OH minus that's gonna really make a big difference. So you do have to do one ice table when you go past the equivalence point in this type of titration. It needs to be in moles. Got to convert it back to molarity because you do need the concentration of the strong base that's left over at this point. And that will get you to the POH and then to the pH. Any questions on that? So in this type of titration curve, there's really 4 distinct parts. First part's pretty simple. It's just straight strong acid right into the pH equation. Second part before the equivalence point, one ice table in moles to figure out how much strong acid you have left over, then into the pH equation. Once you hit the equivalence point, which is the third part, no calculation really needed, just write pH 7 because really all you should have left is a neutral salt. And the fourth part, which is past the equivalence point, one ice table in moles. The purpose of that ice table is to figure out the concentration of the strong base you have left over, which will then get you to the POH and then to the pH. Any questions on any parts of those things?